Okay, so welcome folks. Welcome to the joint webinars by INFORMS-QSR sections and ENBIS. And especially for those of you guys who are currently in the States that do not know about the ENBIS, it's a great society called the European Network for Business and Industrial Statistics. And we have been successfully organizing the joint webinars with ENBIS in the past. So just to let you know that if you're ever interested in the BS, ENBS, just let me know. But also in addition that I do see we have a couple of folks from the ENBS, so welcome. And today we're very fortunate to have Professor James Cohn from Virginia Tech, from specifically the Industrial and System Engineering at Virginia Tech, where I graduated from. Then he is going to talk about the sensing and data analytics for smart additive manufacturing. So before we start, I will remind that you can either ask questions in the chat or comment sections. I can refer them to Dr. Cohn, or you can raise your hand at the end of the seminar. So I will give you, I will let you talk through your microphone so you can directly talk with Dr. Cohn for questions. And lastly, a little bit of background for Dr. Cohn, that he is currently a professor with a graduate department of Industrial and System Engineering at VT. And prior to joining the Virginia Tech, he has been an assistant and associate professor with the School of Industrial Engineering and Management at the Oklahoma State University. He received his PhD from the IC in University of Wisconsin-Madison, and also his bachelor and master's in mechanical engineering from the Harvey Institute of Technology. And then his research focuses on the sensing and analytics for advanced manufacturing and modeling synthesis and diagnosis for large and complex manufacturing systems. Then that his external research funding amounts to over $12 million with a personal share of more than $4 million, sponsored by various federal agencies. Then he has been honored with a number of awards, such as the ISE Fellow, the Dean's Award, and the Outstanding Faculty Award in the past. So without further ado, let's welcome Professor James Cohn. Thank you.
Hello, thank you. Thank you, Yifu, for the introduction, for the organizing this event. And of course, I want to thank the QSR and ENBIS for this invitation, so that I could have such a great opportunity to share some of my research experience with our peers and friends. Okay, as you can see, the title of today's presentation is quite broad: Sensing and Data Analytics for Smart Additive Manufacturing. And today I have quite a lot of slides, and so my talk today it could be a little bit broad rather than in depth. And if you have some specific interest in an area, you can certainly approach me. We can discuss offline for more details. Next page. Oops, why not moving? Yeah, okay. Okay, this a little bit of framework. You can see the focus of my lab. My lab is called Smart Lab. This is a slide I created to show the overall background as well as the collaborative nature of my research. As you can see, usually we start from the material, right? What is manufacturing? The manufacturing is nothing but convert materials from one form to another. So in order to do that, we need to have different manufacturing processes. And nowadays, the 3D printing becomes so popular. This is also my focus in recent couple of years. And in order to actually a QSR, right? So in order to do the quality control, we need to have a sensors like human beings' eyes. Then we need to use different sensing technology. And after that, we may have a huge amount of data, right? So how to deal with those data, these data sets, right? That's supposed to be our ICC expertise. And even we made a critical decision and how to execute it, okay? How to change the process, then we need a control, right? So this is a loop. Okay, so by myself, of course, I'm not able to do it, to do all of them. And even in material science, even in manufacturing processes, in industrial and system engineering, I would not say many, some of the faculty are doing that and are doing excellent work. But as a general expertise of IC, we are more focused on the more centered at analytics, right? So specifically for my area, is centered at analytics and interface with sensing and also with control. But I do have quite a lot of collaborators from material science and from the mechanical engineering, from the electrical engineering. So at Virginia Tech, especially in the College of Engineering, there's a great atmosphere and a tradition of the collaboration. So I have several projects. It's always the multi-departments, multi-colleagues, even multi-universities. And so I can easily like justify the needs, why we need such great efforts, right? So, and also I can use this one to identify my collaborators, right? To showcase my strengths. Okay, so it's outline. At the beginning, the first part, I'm going to introduce the some apparatus setup. And in my lab, I do have pretty big lab, and we have different type of machines. So I'm going to introduce what kind of platforms we have in my lab, and what type of data we can capture, we can collect. Afterwards, the big chunk about the slides are focused on the so-called smart additive manufacturing. And I have two types of data. One is online. Online is the data is being collected during the printing, okay? So we need to make some real-time decision making, okay, decisions. And the second is offline. Offline means, okay, so we do the printing and afterwards we collect data once the printing is accomplished, right? And for example, 3D scanner stuff, right? So for such data, what we can do, okay? Let's end a little bit of summary. So this is a smart additive manufacturing platform focused on metal material. This is what we just accomplished but quite recently. And this is a customized platform. We purchased a simple laser engraver. It's very cheap. And but essentially that's the powder-based platform for the metal material, for example, titanium 64, and also the Inconom stuff. And I think the one great feature is we put a lot of sensors in. We have coaxial, the high resolution camera, and from the top we can observe the printing and at the top, okay. And we have even the oxygen sensors to monitor the level of oxygen. That oxygen is supposed to be lower at a certain level. And also we have the thermal camera, and we have digital image correlation. We put many sensors together. That's almost impossible to be done with commercialized machine. At Virginia Tech, we do have the commercialized SLM280. That's a very advanced machine, but it's so hard to put sensors in. So we just create such a smart metal AM platform, so we can play many things with sensors. This is for the metal material. So this is a relative simple one is for the polymer material, is FDM machine. As you can see, roughly we have the 3D scanner. Actually here, not very clear, but we have also many sensors in, which you can see from next slide. Here we put vibration sensors, we put digital microscope, and vibration sensors installed on the printing bed and also on the extruder, right? So, and it's more like pictures about the sensors, especially for the digital microscope. It's essentially is high definition the camera, and during the printing, we can real time capture the surface, the image of surface that's being printed. Okay, so so the fundamental idea here is, okay, we have the different sensor signals. This is one example of the temperature signal, right? So our fundamental idea is to correlate the sensor signal with the, let me see if I can show my cursor. Are you guys able to see my cursor? Okay, we have different behavior of sensor signals. We try to correlate them with the printing quality. You see most times, of course, maybe the abnormal printing, but sometimes we do see the failure, right? So and are we able to tell without physically looking at those printing and to tell, okay, what's the current status? Is it really normal or some failure happened, right? So some of them perhaps pretty easy even from the sensor signal. You can see here, the signal behaviors very differently. And okay, my cursor disappeared. Okay, but sometimes, most of the time, it's really hard to see anything by eyeballs, right? Of course, we need the help from the data analysis and signal processing. Nowadays, machine learning is so popular. Everybody is claiming we are doing machine learning, right? So all those tools are so helpful for us to perform such a task, okay? To correlate sensor signals, what type of sensor fixtures is so sensitive to capture the printing quality. And hopefully the video is working. Okay, so this is just to show the image-based the online surface quality monitoring. So we have the digital microscope and which can capture in real time the surface of the 3D printing, and then we can perform some the image processing and to quantify or even to classify the type of the operation is normal, failure, or something in between. And also we have thermal cameras. We can capture the part surface, the temperature distribution. And this is very unique. That in our lab, we developed a high resolution of 3D scanner. This 3D scanner can scan either entire part surface or a local area, depends upon our quality requirement. Sometimes we maybe only focus on one specific area with very complex geometry. So we just focus one small region. And this is, although you see these two cameras, this is just components, critical components of the 3D scanner. So essentially there's a structured light based the 3D scanner, which provides the 3D point clouds that can easily, within a couple seconds, provides millions of data points. Okay, each point is X, Y, Z coordinates. Okay, so in the commercialized machine, usually the spatial resolution is about 10 or to 20 micron, which means the pixel to pixel, a point to point distance is 10 to 20 micron. With our further development with some special lenses, so we are able to achieve 2 to 6 micron of spatial resolution, which is very high. And this is some examples to show before and after. Before means the direct off-the-shelf technology. The after is after our improvement by using different special lenses, what we can achieve. The lookalike image, right? Essentially, they are point cloud data. Okay, this is more before and after, with old and new. You can see with our improvement and the spatial resolution was improved significantly. We can observe some features which previously hidden from us. Of course, observe means we need to develop some advanced technology, for example, deep learning, to automatically capture some features instead of the observing manually. Again, more samples to see the before, old and new, and the significant improvement of the scanning. This is another device called digital image correlation. It's still based on this kind of scanning technology by using, but however, previously, what we see the scanning is static. Okay, whatever the part after the printing, we scan the surface to see the surface quality in terms of the millions of the data points. But this digital image correlation is dynamic, which means we can possibly capture the surface dynamic change during the printing, for example, the residual stress and even the strain. So we are able to capture then we can correlate those measurement with the printing quality. And here just show some of the results from our 3D printing using the 3D scanning technology. The first row, those three again, it's not images, they are the point cloud data. They were captured using the white light interferometers, which is very accurate, but it's very time consuming. That's from our the collaborator at UCSB. Okay, they have this advanced equipment and device, and each of the part, I think this part is only 15 by 15. The surface area is only 15 by 15 millimeter, but to scan each of them need about a couple hours, which is very, very time consuming. With our structured light scanner, for each surface, we only spend like 10 to 20 seconds. And however, it's much, much faster. And the result in terms of surface finishing is still, of course, there are some errors. We're still in the process of improvement, but it's reasonable. And some of them quite close. And for different scanning, at the top, you see raster block, D-half block, and the random block. That means different patterns of the scanning, different scanning for the, different patterns for the printing. For example, during the printing, the laser have different way of scan, right? So different patterns. And the second row is is captured by using our scanner. You see some of them quite close, some of them little bit error is a little bit larger. But the relative, which one is the best, which one is the worst, is consistent with the white light interferometer. We can consider interferometer is kind of ground truth because it's so accurate, but it's so time consuming, right? So each part needs a couple hours. So no way to apply it, and also the device is quite big. No way to integrate with the 3D printer. With our 3D scanner, it is possible to put together with 3D printer. Right, so it's very cost effective, and the precision and accuracy is also acceptable. The last column, last row, the images shows the DIC, digital image correlation, shows was a strain released, right? Which a strain released directly related to the quality of the 3D printing. Okay. So far I introduced the different platforms, different 3D printers in my lab, and they are all pretty cheap solutions, not expensive. Even for the metal one, it's customized, the simple one. We only spent like $30,000. Okay, $30,000 for that platform, and the printing capability is quite limited. But the uniqueness is that we are able to put a lot of sensors in. We are able to capture a huge amount of data, either in real time or offline, right? The next question is what we can do, right? Then it's time to showcase our IC department's capability, right? So the first part is online data, right? Online data, and means the data will capture during the printing. So instead of as opposed to the offline, okay? So the one thing is in one of our publications, and we use the manifold learning to extract, to do the feature extraction, right? Manifold learning, we can consider it's it's non-linear PCA, right? Which can capture the inherent structure, the spatial structure for high dimensional data, right? So many of you guys may be an expert in this area. I'm not going to introduce in details, and but later on, I'm going to showcase the result of using manifold learning for feature extraction, and then the extracted features can be used by us to do the supervised classification, or sometimes just the SPC control charting. This is another technology we are using. It's so-called graph theory-based image analysis. We can use that one either to image analysis or point cloud data analysis. So at the top, we can see two surfaces. They are captured from the printed surface. our basic objective is how to quantify the variability, right? And surface image data is nice and can tell us many things. However, it's the high dimensional data, right? Even like 10 by 10, I'm sorry, even 100 by 100, which is quite small image. The total number for pixel is 10,000, right? So how to generate, let's say, how to generate one single number to represent the variability of entire surface, right? So in the industry standard, there is something in GD&T or something in surface quality called the surface finishing, right? RASA stuff, which can be used, but which is very localized. We want to develop something more global, which can capture the variability of entire surface, but with single number, right? So then this the basic idea is, and we create a graph. Those graphs, we have a number of nodes. These nodes, they are sitting at the circle, okay? And let's assume if a surface is perfectly flat, okay? Perfect flat means all the pixels, they have the same value. If all the pixels, they have the same value between any pair of them, they are identical, right? Then we just connect them, right? They're identical, they are so close. Identical means they are perfectly the same, right? Then we just connect them, right? For example, connect from this node to this node. Okay, if for a perfect surface, all the pixels, they are the same, then all of them are connected, right? Then we are going to see a very dense, the most dense graph, because all the nodes at the boundary, they are connected. Let's think about another surface which has quite a big variability, which means many of the pairs of pixels, their value is so different. If they are so different, we are going to disconnect them. So we are not going to connect them. Then you will see some of the pixels, they are not connected. Then we are going to see a loose graph, right? Then in graph theory, there are many nice properties sitting in the graph theory, the literature for many years. We can utilize them to quantify the density of these two graphs, okay? Then the density directly related to the variability of pixels, the variability of the finished quality, the surface quality, right? That's the essentially more specifics called feeder number. Feeder number, we can use the feeder number to quantify the density, to quantify the surface quality. We also have the paper published in these topics in the IIC transaction. Okay, so the third topic is very challenging, is quite interesting, is the thermal image data fusion. Actually, not necessarily thermal image. Any of the image, we can do the data fusion. The motivation is directly from our experience of our experiments at Oregon National Lab. This is the Oregon National Lab at Chicago suburb. We went there to perform some of the metal AM, the experiments, but we are facing the difficulty of the thermal data, the collection. We have this left-hand side is a thermal camera we have in my lab. You can see there's a camera 2 from Virginia Tech, and the spatial resolution is quite high. It's 3 to 10 microns. It's very good. However, the temporal resolution is so poor. It's just 1 kilohertz. 1 kilohertz. We do have another camera, very advanced camera from Oregon National Lab. The spatial resolution is quite. The temporal resolution is quite high. It's 20,000 kilohertz, but the spatial resolution is pretty low. It's only 30 micron. The reason was, you can see here, this is the also customized 3D printing, metal 3D printing platform. You see the red area is a chamber for the printing. This is a big, this one enclosed by this the yellow color rectangle. This is advanced camera, thermal camera from Oregon National Lab. Because it's so bulky, it's pretty big. It's no way to put this big camera inside of the this chamber. So it needs to stay far away. This is the reason its spatial resolution is quite poor. Okay, our camera is very compact. We are able to install this camera inside of this chamber. So this the M1, this micron epsilon M1, the camera can stay very close to the printing area. This is the reason its spatial resolution is quite high. Okay, however, so neither of them is perfect. Okay, for our camera, the spatial resolution is good, but poor the temporal resolution, and the camera from the Argonne National Lab is exactly opposite. We really want to see, are we able to have some sort of data? Okay, spatial resolution is close to 3 to 10 micron, but the temporal resolution is 20 kilohertz, right? So then we need ask ourselves, okay, we are not able to achieve such the goal directly, but can we do some sort of image data fusion to combine these two video sources together to achieve that goal, right? Essentially, it's kind of to use cheap sensing technology to very cheap one, relatively cheap ones to achieve very expensive data. Okay, so this is a kind of motivation using the tensor, because the scanned image data, they are image stream. Image stream, naturally, we can treat them as a 3D order of 3 of tensor. So we have 2 image streams. The top one is high temporal stream, and but the spatial resolution is low. We can see small images, right? And the lower one has higher spatial stream, higher spatial resolution with the bigger images, but you see the temporal resolution is low, right? Our basic idea is we enlarge the image with lower spatial resolution, and then insert higher spatial with higher spatial but low temporal image, insert in between of the higher spatial ones. And then we can have something like this. But the problem is for the enlarged image, okay, so we enlarge it so many pixels, actually we don't have their value, right? It's kind of missing value. Then we can use the tensor completion to help to approximate those missing values, right? So by using tensor the completion. So our basic idea, we assume in the thermal image, we have some smooth features, we have some sparse features, okay? Then we can use the tensor completion to approximate those the smooth and sparse components in the images. So so basically, essentially, this Z is our tensors have 2 components. And this is the first part is sparse, second part, first part is smooth, second part is sparse. And we do the least square regression, and we use the Z. Z is our tensor to approximate our X. X is our actual images, videos, because we have several image coming as videos. And also, apart from the residual errors, the penalty, we also have the penalty from the smoothness components and the sparseness components. Right. This is a very high level description. I'm not going to talk about in details about this kind of the formulations. That if I'm interested, we can discuss more. This current paper is current review. It's being reviewed and also received very recent last November, the best paper award is one of the finalists. Okay, I skip those details. With the more illustrations, we use case study from the X-ray images, and you see the bigger one, the bigger image X-ray, bigger ones means what? High temporal. I'm sorry, high spatial but low temporal. Many small ones in the middle means high temporal but low spatial, right? So we enlarge them, merge them together. We use tensor completion to get to fill the missing values, and a little bit the illustration about our results. And the first one, the RSC is the lower the better. You see the lowest one, the dash red is our method, And another is the peak signal to noise ratio. The higher the better. Our method achieve also the best performance. Okay, and also we did experiments in our lab. We used two different cameras with the complementary specification in spatial and temporal. We try to combine them together, and we did the performance. We did experiments and also analysis. Compare our method. Last column is our method compared with all. I think with all the other popular benchmark methods, and our method achieved the regarding the data fitting performance is the best, but it's not the fastest one. The not faster one. The running time, this method is the faster one. And also we can showcase of one tensor completion result. The first data, the first one A here is the actual image, okay. And the second one is the using tensor completion what we approximate, and the image is approximated by using the tensors has two components. One is the smooth components, another is sparse components. The sparse components you can see this blue the spot here. This is corresponding to the experiments, the heating area. We heated from this area, but it was successfully captured by the sparse components. Okay, again, some other online data. For example, during the 3D printing just now, I showed that we are able to capture the video directly during the 3D printing, right? So we apply many transformations, and this is our the strings. And one of the transformation we were using is called half transformation, and it's one very popular method in signal processing. By using half transformation, we are able to just generate one number to represent surface quality, and we can use this one to design some sort of the control chart to capture the surface defects. And also, this is just some of the examples of the surface we captured during the 3D printing. And you can see the first row is normal printing. Second row, we have some sort of defects, is overfilling too much material. The third one is underfill, is the material is not sufficient, right? So instead of the observing manually, so we can use different image processing technique or high dimensional data analysis to classify, right? Then the supervised classification can play the role, right, for based on the image data. Okay, this is the result we achieved by using the manifold learning, right? Manifold learning, what we are focused is just small image, which only 80 by 80 pixels. 80 by 80 pixels is 6400 dimensional, high dimensional data, right? We use the manifold learning to extract just one single number for the the manifold learning. We can consider sort of nonlinear PCA. We only keep the first PC, and we use that first PC to conduct the SPC control charting, and it was successfully capturing the defects during the printing. It's very interesting. Okay. And this is more data to showcase our developed the manifold learning based classification for quality control. So we can see the F score of our method is highest among all the popular methods, and also the speed is very fast. Is the what we need, just like 1 second. 1 second, so basically it's quite fast. It's possible to apply it in online application. Okay, so we also implement some simple closed loop control by using PID controller, and I would like to show this already published in IC transaction. No, the Journal of Manufacturing Systems. I just want to give you one example. In our 3D printer for the FDM, for the polymer one, there is a control for the cooling fan on-off, But that one, by default, we can only set it once. It's only either always on or always off. If the cooling fan is always on, the temperature eventually will be too low. But if the cooling fan is always off, the temperature, because lack of cooling, the temperature eventually will be too high, right? So we developed a PID controller which can automatically, monitor the temperature, and we implement the closed loop control. If temperature is relatively high, we are going to turn on the cooling fan. Otherwise, we are going to turn off. Right? By that way, the temperature within the chamber can be maintained in the desired area, in the desired range. So then we can achieve a satisfying the surface quality. Okay, so the next couple of slides is introduce an interesting area is in the AM cyber attacks. So this is the problem description. Okay, I want to showcase this part. This is a part. It's a part that we printed using our 3D printing. It's polymer material. Okay, but they looks the same. Looks like identical from their external the appearance, but internally they're different, because the attacked one means there is a hole. Because we can imagine a hacker can log into our computer and insert undesired hole into the our str the data file, and then the slicing software will do the slicing G codes from this str file, but we don't know it. And then when we do the printing and after printing, we are not able to observe it at all from the appearance. So what we want to do is, are we able to, let's simply say, using our classical technique of the SPC control chart. Okay, during the 3D printing, are we able to develop some sort of SPC control chart based on the sensors to detect, okay, there is something wrong during the printing. Okay, so along this line, we develop putting the different some vibration sensors. Okay, and then again we use this graph theory to develop to extract features and develop the SPC the control chart. This is not control chart yet, and this is just the to plot the features we extracted to see, are we able to separate the normal parts and attacked parts. You see the stage 1 and the stage 3, these two type colors, normal and attacked, they are so overlapping, right? It's almost impossible to separate them. But in stage 2, they are pretty much kind of the good separation, right? This is our observation in stage 2. And then we develop, again, using the graph theory-based method. Graph theory-based method, a couple minutes ago, I introduced how to use that one to do the image analysis. Actually, it can be used for any of the multivariate data. In this case, we use graph theory-based method to extract features, and then we can see we use the SPC control chart. We can well separate the attacked parts and normal parts, which means if the part is really attacked, which has a hole inside, it was successfully detected. But for the part which is still normal, there's no false alarm. All right, this is just very initial analysis, and but we do see the greater potential by using some sort of interesting feature extractions combined with our classical SPC control chart. We may do something very useful for the advanced manufacturing cybersecurity related topics. Okay, so just now I introduced the online data. Okay, online data means the data were captured during the printing. Okay, the printing is still going on. Next couple of slides, I'm going to introduce offline data. So the offline data is after printing. We do either the scanning and or some X-ray analysis, right? X-ray scanning. So then to have the very thorough inspection for the quality. So the first one is micro CT. We use micro CT, scan the parts and to see the patterns of the porosity. Porosity for metal printing is what we really do not want to see, okay? And in the bio printing, perhaps that's what we want to make the biomaterial more similar to the actual material with some porosities. But again, for the metals, we do not want to see it. And this is a part was fabricated by my collaborator, Dr. Chris Williams at ME department of Virginia Tech. And it is the mushroom, okay, with the you can see different scannings and different layer by layer scannings. And then here I just captured this rectangle area. We show all the layer by layer frames and almost like a video. You see the lots of black dots. They are the porosity. This size varies. So some of them may be 10 microns, some of them may be over the 100 microns. And we developed methods and to capture the density of each layers of those porosities. We use the log normal, the Cox process modeling, and also combine the size of the porosity. So instead of this raw data, in the raw data, we can see some sort of patterns. At the beginning, okay, the porosity is not that much, and eventually increasing and increasing, and also decreasing, right? It's a layer by layer. But now we are using the statistical modeling. We can precisely capture the spatial and the temporal, the correlation. Because layer to layer, they have some sort of like a temporal correlation. Within each layer, we do see this strong spatial correlation, right? So this piece of work published the IIC transaction. And then if we can, for each layer, if we are able to evaluate the average intensity. You see this red color means high risk of high intensity or high risk of the porosity, right? The blue color means low risk of porosity. Then for each layer, we estimate the average intensity. Then we plot the intensities along the different layers. We can see at the beginning, okay, the porosity was not that severe. At the middle, it's pretty bad, okay, pretty high level of porosity. At the end, the layers, okay, also decreasing, right? They have quite a strong the spatial layer by layer spatial correlation there. So we can share this one with our domain experts. For example, share with my collaborators and from the mechanical engineering. They can think about what happened in the middle, right? What happened in the middle? This is also a very interesting example to show. In the 3D printing, we should not just use one fixed set of the printing parameters. Perhaps we need to change in the middle. This also shows like in 3D printing, our classical just one set of DOE may not work. At least several sets of DOE, right? But to simulate the printing in the middle layer is quite difficult, right? Then closed loop control is really necessary. Okay, so how much time? Okay, so 45 minutes. I only have just a couple of slides left. I will give a quick summary without the details. This is the scanning data. Again, this is the 3D scanning data for you can see the 1, 2, 3 parts. These parts you can see that there are a lot of small features, right? And this is standard part. This standard part standard part with standard features designed by NIST. They purposely design different type of features, and then we print these features. We can measure those features to see the performance of the 3D printing. Okay, this is collaborative work with Oak Ridge National Lab. Okay, they printed the same part with different materials and with different platforms, and then they scanned it. So each part they scanned, they printed 3 parts with 3 scannings. Each of them has 500,000 data points. It's around 500,000 data points. They did not tell us what's the material and what is platform. They just labeled as part 1, part 2, part 3. Okay. They already have some quality inspection result, but they want to really test the performance of the graph theory I introduced a couple minutes ago. Okay, we use our method, the graph theory. This is a review of graph theory again. I just skipped it. And then use the feeder number. The feeder number is the lower the better. Lower feeder number means the better quality. And through our analysis, we show that a carbon fiber with ABS platform achieve the best. ABS platform, the quality is the worst. ABS chamber is something in the middle, right? At that moment, we did not know what the material is. We can only tell, okay, this data set is the best, this data set is the worst, etc. And then the researchers, our collaborators at the Oak Ridge National Lab, then they tell us what this one is, what material and what platform. Our analysis is pretty much identical with their discovery. So they were quite happy with the performance with our graph theory based method, and we co-authored one paper published in the SME transaction of the Journal of Manufacturing Science and Engineering. Okay, so good timing. So again, this is the my summary slides actually is the same as my the first slides almost, the framework. So I highlighted the analytics part in the red and the green. So this is a key, actually still a key area of my research. And I do believe this is also the key capacities of our IC department for most of us, although we do have some great experts in material and manufacturing processes. Again, and so especially for junior faculty members, you may look at this kind of framework to see what is really your strength and what is in your department, in your colleagues, and what type of resources do we have, right? And for additive manufacturing, and for most people, including myself, I do need collaborations. I do need people from different areas, right? We can also use this one to identify the potential collaborators. Okay, so I think this is all of my talk, and any questions? I do see one in the this one. How this aggregated data is used to control the printing itself, like stopping. So the data actually we need to do some offline. Although I claim that the online quality control, right? Online real time, we do need some offline training. So it's kind of labeling. It's kind of labeling. For example, we have different classes, and each classes through our analysis, or either by using sensor inspection, or like even the visualization, we need to label them, and basically follow the procedure of the supervised classification. Right, that part I did not mention, but the tedious work and for the labeling. Do you think material science aspects should be integrated with the printing? Exactly. This again, the question is, do you think material science aspects features should be integrated with the printing features? That's exactly what we need to pay attention to. So we claim many things about data-driven, right? Data-driven, but essentially we want to provide some information useful for the material science area, essentially, especially for this area. So material science, they are emphasize the printing parameters and the structures of the material and the performance of the material, right? So do not forget, do not overplay the data-driven. Data-driven is powerful, particularly if we do not have a thorough or high fidelity of the physical data. But at the end, we need to provide useful information to material science regarding, for example, the relationship between the microstructure and the material property, right? And the relationship between the printing conditions, printing parameters with the microstructure, right? So So we are able to, with IC strength, or even like talk about the entire INFORMS, not only IC, right? Computer science and even the civil engineering, the business school. And we are so good and we are so powerful in terms of the modeling. Those modeling can provide those correlation, provides the relationship between the one quantity with another quantity. But do not forget what is our application domain. Okay.
Yep. Any other questions? Actually, Dr. I have a question. Yeah. So I think I remember that you were saying that the resolution is about 3,000 by 4,000. Right. Then I'm curious that do you ever encounter the problem that you can actually not model the original resolution due to the low memory or some similar problems?
So memory is not the issue. Actually, nowadays our computational power is quite high. But there's always a resolution issue. And resolution, for example, sometimes like that depends upon our scope. For example, if I want to scan the entire surface, like in that example, in our experiments, the entire surface is 15 by 15 millimeter, right? 15 by 15 millimeter. If you want to scan the entire surface, the resolution can be easily calculated. It's just like 15 by 15 millimeter, which is what, 15,000 by 15,000 micrometer, right? And divided by 3,000, right? 3,000. But that spatial resolution is not high enough. Mm-hmm. Right? So then in order to do that, we need to really make the field of view. Field of view is what the camera can see. So we need to make the field of view quite small. So instead of scan the entire surface, the 15 by 15 millimeter, I want to only look at the 2 millimeter by 2 millimeter, such a small area. Then the spatial resolution can be improved significantly. Right? In our application, actually, if I remember correctly, what we did is the, let me do a little bit of calculation. It's 2 millimeter by 3 millimeter by 3 millimeter. And think about if like, assume it's 2 millimeter by 2 millimeter by 2 millimeter with such small area, then divided by like 3,000 pixels, that spatial resolution is much higher. Yeah. But we are facing difficulties. Our off-the-shelf, the scanner is not able to focus on the 2 millimeter by 2 millimeter small area. Then we need help from the special lenses. Right? We not only just use the off-shelf camera, we also install some special lenses. The difficulty is the special lens can be easily purchased, but the entire structure of the 3D scanner, the calibration, entire things need to be redone. Okay, that's a part of one of my students is doing. Actually, it's your friend Raphael Wang. He spent a lot of time to figure out how to redo the calibration for the 3D scanner, which was successfully implemented. Right. So again, the spatial resolution really depends upon the field of view. Field of view is the area we want to see. Right. We want to see the small area, so we can have the great the spatial resolution. But the spatial area is so local, right? If we want to see the entire big area is global, that's great. However, the temporal spatial resolution will be poor, right? So that's a trade-off, right? Okay. I also see one question. Thanks. Yes. You only use the first PC for a few slides back, simple because you know the components has great variance. No, yeah, that's true. That's true. I just just demonstrate. Of course, the how many PCs we need to use also kind of like art type of job. I do have some quantification to the first one, first two, first three. But for that specific case, even with the first PC, the performance of the SPC control charting, we are just because it's just a good or bad, right? It's two-class classification. I just use SPC control chart. The performance is pretty good, which means the data has very strong spatial correlation. Very strong spatial correlation. We use very small number of PCs. Even first PC captures the majority of the variability, which we can use SPC to do the anomaly detection. And even it's not even we have 2 or 3 or 4 PCs, we can use it. Even simple the multivariate control chart, we can achieve the similar goal, right? So and the feature extraction is pretty powerful. After feature extraction, the remaining of classification is very simple, right? Let's look at the deep learning, right? Neural network. The majority of tasks in the feature extraction part, different layers for the feature extraction. And the very last part of the classification is just simple softmax, right? So that's simple, right? Right, so the simple logistic function, right? So it's pretty simple, but the key is feature extraction. So we all play different games for the feature extraction. Okay, and then
any other questions?
Okay.
You may also raise your hand if you want to directly say out your question.
Did I miss anything? Okay.
Okay. Okay. So Dr. Cohn did talk a great amount of the stuffs in the recent advancement in additive manufacturing, all the way from the scratch about the collecting of data, all the way to how do you handle the data. And it's indeed a very interesting talk. So if we do not have any other questions, we will see each other in the next webinar. Again, thanks to Professor James Cohn for coming to today's meeting. And
thank you.
Last but not least, also thank Bess for being helpful to hosting the meeting as well. Thanks, everyone. And thank you, Professor Cohn.
Thank you. Thank you for your attendance.